Hello and welcome to Chapter 6. Chapter 6 is inference again. Sounds familiar, right? And now we're switching gears to categorical data, right? And so I want to highlight that because remember in Chapter 5, we were talking about numerical data, right? So we need tools for dealing with numerical data, and then we also need to develop some tools for dealing with categorical data. So, right, so far, we've talked about population means, and this is from chapter 5. Right, chapter 5, which was numerical data. Right, that's when we talk about the mean. But now, our questions are going to be about the proportion. Okay, so the proportion, that's for categorical data. Well, maybe a better arrow there. Good, not great. Okay. So the proportion of some outcome in a population. So in, I want to say chapter 1 for sure, and in chapter 2, we talked about, okay, well, proportions can be reported as percentages, right? But they're the decimal between 0 and 1 is a proportion. And proportions are also probabilities. But now we'll have probabilities about the proportion, so it can get a little bit sticky there. But as long as you remember that we're talking about proportions, you're okay. So everything that we've learned so far, we're still going to use. And I'm thinking specifically about the Z-scores from before. We use t-scores, so t-tests for chapter 5 for numerical data as soon as we're talking about a mean, whether that's comparing one mean to some hypothesized value, or if it's matched pairs situation, then that's still one mean. Or if you have two independent sample means that you want to compare, those all use t-tests. Okay, whereas now for proportions, we switch back to z-scores and z-tests. So that's kind of nice. The calculation is a little bit new, but the z-score itself we're very familiar with and hopefully very comfortable with, right? And so everything that we learned for hypothesis testing, confidence intervals, we just need to build on that. Our hypotheses will change a little bit because they're going to be about the proportion, right? The population proportion. But what's really nice is that sample proportions follow a nearly normal distribution when certain conditions are satisfied. So I want to highlight that. And so here, we need to check assumptions, which we haven't really been doing. We've kind of touched on it briefly. Oh, was our sample randomly selected? Okay, great. Is our sample size large enough? Okay, that's good, but not too large, right? So we kind of touched on it. We didn't emphasize it very much, but now in chapter 6 for proportions, it's going to be really important. And so we need to check assumptions for proportion questions. Proportions, yikes. Proportion questions. Okay, so that's going to be a little bit new, but it's important. Okay, and from there, if the conditions are satisfied or the assumptions are satisfied, then we can go ahead and use the Z-score. But if you kind of take a step back and think about, well, categorical data are things like how many people answered yes and how many people answered no to some question. Right, and so you've got these proportions, right? 45 out of 100 said yes, 55 out of 100 said no, right? That kind of thing. And so how do we get those proportions to follow a normal distribution. They do, and that's really cool and really powerful, but that's why we have to check the assumptions, is because it's not obvious anymore. Okay, so some notation that we're going to use. Before, right, I was using Greek letters for anything that has to do with the population. So any parameter, I was using a Greek letter. Whereas for proportions, I tend to just use a lowercase p for a proportion, and that indicates a population proportion. You can use pi. It's just that we use pi as a numerical constant, right? And so then it gets a little bit weird. So I use P for the population proportion, right? But if you want to stick to having all Greek letters for anything that has to do with the population, then you can use pi, but I'm going to use just a lowercase p. And then we have p hat. P hat is the sample proportion, okay? Before, right, we were using things like x bar, but anything with a bar over it means that it's the mean, right? So anything with a bar over it is an average, a sample average. So we can't use p bar because that would be the average of p, and that's not what we want. So we need some new notation, and that's where this p hat comes in. Okay, and so p hat is used to denote the sample proportion. Okay, so that's the proportion that we get from our sample. Okay, so I'm going to go into more detail, but I want to bring in the formula sheet section for one sample proportion. I've got it down here, just so we can have a look and just kind of pick through this, because my goal is for you to look at this, and even though you haven't done a proportion type question, this is for one sample proportion, right? So 4 out of 5 dentists recommend Colgate, whatever. That would be a one sample proportion. So even though we haven't done anything like this, right? My hope is that when you look at this, maybe excluding the sample size calculation, but even that is not that bad. Okay, so you can ignore I'm covering it with my hand, but you can't see that on my iPad. But so kind of ignoring this for now, right? When you look at the formula sheet, it doesn't look that bad, right? We're using a lot of the same, and like I said, we're going to go into more detail, but I just want to show you that, hey, we've actually built up quite a few skills already, right? And so I know you're thinking, already, it's the second to last chapter. I know. We've still got some time together. So your null hypothesis is going to be that P, remember P is the population proportion. Okay, P equals some P naught, just like mu naught was a placeholder for some number. That's exactly what it is for P naught as well. So where P naught is a placeholder for the hypothesized proportion. Hypothesized proportion, we want to compare, the sample proportion to. Oh, man, that looks bad. Worse. The sample proportion to. Clean up compare here. We can do better than that. And by we, I mean me. Okay. So P naught is still just a placeholder for some number. And of course, the alternative hypothesis by default has the not equal to, but it depends on the question. Okay. Then I want you to look at the z-score. So it's exciting because we see a Z. Okay, so now we have to go back to the Z table. And you might be feeling like I was trying to convince you of before you started using the T table. When we first introduced the T table, I said, well, typically people kind of come around to the T table because it's so much kind of briefer and I think easier to use than the Z table. So now going back to the Z table feels like, if it doesn't, then that's great. But for me, it always feels like, oh, back here, ugh. But it's nice and familiar, and we know how it behaves now, so that's good. P hat, we know, is your sample proportion, right? P naught is, of course, your hypothesized proportion. And then notice that P naught appears again, right? Q naught, you might remember from when we talked about the binomial, right? Q naught, so Q is just 1 minus P. So Q naught would be 1 minus P naught. And then divided by N and then square rooted. So N is the sample size still. Okay. We can build a confidence interval. So again, we have P hat from the sample. We know how to find Z star. P hat again, right? And then Q hat is just 1 minus P hat over N square rooted. One thing I will alert you to is that in the past, this square root, so whatever's in the denominator of your test statistic has been the same as what's the standard error, or it's always been the standard error, but these aren't the same anymore, right? So that's kind of a heads up for proportions, is that we tend to use, or we do use, different values depending on the scenario. But as long as you have the formula sheet, you're safe, right? Just follow the formula sheet. But notice how we don't need a lot of information here, right? We need P hat, P naught, and potentially N. Usually N would be given like, so 30 out of 100 students. So 30 over 100 is your P hat, and then you have N in that information. So what's nice about proportions, even though they're so kind of foreign feeling right now, the questions tend to be easier to read because we don't need to give a lot of information to be able to solve them. Okay. We've done sample size calculations before, right? We're going to do them again, and this one is kind of more relevant for proportions. So when we're testing proportions, we're typically working on survey data and collecting information from the public. And so then it's really useful to know what sample size we would need, right? And so this sample size calculation is the more important of the two, right? But we've done it before, so we have some core skills already. Okay. The only thing we don't know, we know what Z star is. M is still going to be the margin of error. And the only thing we don't know about is P star, Q star. Q star is, of course, 1 minus P star. But what is P star? You'll have to stay tuned to find out. It's at the end of the part 1 notes if you're interested, but I want to hold off. So there's really nothing, well, everything is new on the formula sheet, right? But there's no new concepts here. It's just new information that we need to deal with. All right, so let me organize these notes here. Okay, so at this point, it kind of goes without saying that, of course, we're going to use the sample mean to try to learn something about, sorry, I said sample mean. I'm stuck in chapter 5, guys. We're going to use the sample proportion to try to learn something about the population proportion. Okay, so P hat is the sample proportion, right? So just like before, yeah, in section 3.4, where we talked about the binomial and we calculated binomial probabilities, we're going to define a success as whatever we're looking for, right? So it's not necessarily positive, as we saw, right? It's typically kind of negative, but we'll call it a success because that's, what we're interested in. Okay, so the sample proportion, how you're going to calculate it is it's the number of successes in the sample over the total number of individuals in the sample, of course. And then use the decimal version for your calculations. Or you can use the exact fraction if you want to, but then it tends to get kind of boggy. So usually I calculate a decimal and then I round it to 3 or 4 decimal places, and then it should be okay. So the sample proportion, it'll either say something like, so the question might say something like, 87 out of 250 doctors said this, right? So then what's your number of successes? Well, it's 87 out of 250, right? And so that would be your p hat, right? And then you could convert that to a decimal. So that would be your sample proportion. It could also just be given as 37% of doctors said this. I don't know if those are matching, but I'm just making up numbers here, right? And so it could just give you a percentage, and then you would have to just convert that to a decimal, of course, and then you would have the sample proportion that way. So we've seen this before where, okay, each sample that we take, we understand that with each new sample, even if we're randomly selecting every time, the sample mean is going to change depending on our sample, right? Not change a lot, hopefully, but change a little bit. There's a little bit of movement, and that's where that sampling distribution came from, right? And so in the same way, when we take a sample and we calculate a sample proportion, we understand that if we took a completely different sample, even if it's perfectly sampled, if we took a different sample and we calculated the sample proportion for that sample, then of course we would find a slightly different number. But we expect them to kind of hang around the same values. And so there we get a sampling distribution for the sample proportion. Okay. So I want to just kind of we're going to get to the assumptions. And the assumptions are the important part. But on the side here, I have just the background of why this is going on. It feels weird to not talk about it, so that's why I'm going to mention it briefly. It's not something that I expect you to know explicitly. I want you to know to check the assumptions, but that's about it. But I do want to talk about it just briefly. So if we draw a simple random sample, right, an SRS, simple random sample of size n from a large population that contains a proportion p, so the population proportion of successes, and then we're going to let p hat be the sample proportion of successes, then the mean of the sampling distribution of p hat is just p. So okay, if we think about it, okay, so I've collected samples and I'm recording the sample proportions, then I expect them to be centered on the population proportion, right? That feels weird initially, but then when you kind of talk it out, it makes sense. Or maybe just to me, it makes, anyways. Like I said, this is just theory, so you kind of have an idea of where things are coming from, but it's okay if you want to tune out for 2 minutes here. So the standard error, why am I even saying that then? No, it's important. It's where it's coming from. So the standard error of the sampling distribution, so of the sampling distribution of p hat, is going to be p times 1 minus p over n and then square rooted, where 1 minus p is often denoted as q. I like to use q because it kind of cleans up the calculation a little bit. But if you want to replace all your q's with 1 minus the equivalent p, then that is totally fine. So then as the sample size increases, right, so we need a large enough sample, the sampling distribution of p hat becomes approximately normal, right? And so we get these population proportions and they start to fill out and they start to look like a normal distribution centered on p with a standard error, which happens to be the root of p times 1 minus p over n, where p is the population proportion. Right? Which happens here and here as well, right? Okay, so that's kind of cool. We're going to use this, but I'm not going to test you on it explicitly, like I said. I will test you on checking the assumptions. So there will be a written question where you have to check the assumptions and what are the assumptions. Some of these are going to feel familiar from when we did those binomial questions, but we have a couple of other things to add on. And just, okay. So like I mentioned earlier, we have to check the assumptions just like when we were going to use the normal approximation to the binomial, which is where we ended the binomial section. So, and that was a while ago, right? But just like we had to check the assumptions there, now again, we have to check these assumptions. So here we go. We always have to check that we have independent observations. Now, there are two things that we need to check in that category. To make sure that we have independent observations, we have to have a random sample. Usually that'll be stated. If it's not stated, right, then these are assumptions, right? Then you need to say that, hey, I'm assuming that this sample was selected randomly, even if it doesn't say that. That is something that we're assuming happened, right? The second thing, and I feel like we've kind of touched on it, but not explicitly. So the 10% condition says that if sampling without replacement, so you're not, putting people back into the population, once they are in your sample, they stay there. Your sample size has to be less than 10% of the population, which seems weird, right? But we've seen this before where we want to have a large sample. Yeah, bigger, better, best. But not too big, because then you lose that independence, right? You're more likely to sample siblings or whole families or, dependent observations, depending on what you're talking about. So what we need to check or argue, right? If it's not obvious from the question, it is something that you're assuming, so you have to argue it. Then you have to check that the sample size that you have doesn't make up more than 10% of the entire population, right? So you want big samples, but not too big. Usually it's not a problem, right? Usually your sample size is not more than 10% of the population, so that's usually fine. The second set of observations, so I break them up to kind of two categories, right? So here first you have to check that you have independent observations, and there's two sub checks in there. And then the next check that you have to do is for normality. The normality assumption depends on if we're doing a hypothesis test or a confidence interval, and that's really kind of hard, right? But it is what it is. We just have to deal with that. Okay, so it's going to depend on whether we're doing a hypothesis test or a confidence interval. So for proportion question, as soon as you've decided, okay, this is a proportion question, great. I know I have to check my assumptions, good. Then I would encourage you to read the entire question and see if you have to do a hypothesis test or a confidence interval or potentially both. Because if you're doing both, you may as well just check all the assumptions right away and get them over with, so to speak. And you don't want to check more assumptions than you have to, right? So if you find that you're only doing a hypothesis test, then you only need to check the hypothesis testing conditions. And if you're only doing a confidence interval, then you only need to do check the confidence interval conditions. So for the hypothesis test, we actually have the same criteria as we did for the binomial, right? Which was that we have to have at least, oh, now I'm blanking. Sorry, the confidence is the same. The confidence interval is the same as the binomial. Erase what I just said. And sit on it until the confidence interval. Okay, so for a hypothesis test, we need at least 10 expected successes and failures, which we calculate using the null value, so the P naught from the null hypothesis, right? And so you have your sample size times P naught. So that's how many successes you would expect to see under your null hypothesis, right? And then N times Q naught is just N times 1 minus P naught, right? Which is the expected number of failures. And both of those have to be larger than 10. It gets confusing because here we have N has to be less than 10% of the population. And here the number of successes, or the expected successes and the expected failures, have to be more than 10, a count of 10. Okay. Whereas for confidence intervals, you need at least 10 observed successes. And this is the same as for the binomial. Right, so we've seen this before where we need at least 10 observed successes and failures. And how do we find that? You could use N times P hat if you're given P hat, right? Or you could do, if given the number of successes in the question, just use them instead of N times P hat, right? So if you're told that 87 out of 250 teachers said something, I don't know, then 87 is the number of successes, and then 250 minus 87 is the number of failures, right? So it's important to remember that Q is 1 minus P, or the probability of a failure, right? And so Q hat is 1 minus P hat, Q naught is 1 minus P naught, Q star is 1 minus P star, but this is just summarized as Q equals 1 minus P on your formula sheet, right? And so here I'm just gonna do a subtle highlight here because it tends to come up, right? People are confused by the Q, but you shouldn't be. It's just 1 minus P and whatever the P is. All right. So those are the assumptions. So it's kind of tricky because for the normality condition, it depends on what the question's asking you for. And I should add, if you're doing a hypothesis test, it does require you to set up your null hypothesis, or at least figure out your hypothesized value to use it in your assumptions, which you do the assumptions before you actually do any calculations or state the null and alternative hypotheses formally. So that's kind of weird, but It's given in the question, so you'll have it, but yeah, but you still need to use it. All right. Let's talk about hypothesis testing for one sample proportions. So in the next part, we're going to talk about comparing two sample proportions. So now I've collected two samples and I want to compare those proportions, which is very similar to when we talked about two sample means, right? And so we're starting here with one sample proportions. So the idea is the same, right? First thing we have to do is we state our null and alternative hypotheses, right? And so what we saw in the formula sheet was that our null hypothesis is that P equals P naught, right? And so where P naught comes from the question. Okay. Step 2, we have to do the test, and we're calculating a z-score, and it's because p hat follows a normal distribution with a mean of p, right? If we kind of think back to recall, if x bar follows a normal distribution with a mean mu and a standard deviation of sigma over root n, then z equals x bar minus mu over sigma over root n. So notice I'll use the same colors here. X bar to x bar, p hat to p hat. Okay. New color, mu to mu. Right? The mean of p hat is p, and here I've got a p naught, but p naught equals p, right? So that's not that big of a stretch. P is p naught. So here we have p naught. And then of course, if p equals p naught, then this could be replaced by p times 1 minus p over n, right? So it is the same. And these are the same, right? So notice it has the same structure. It's just that now we're talking about proportions, right? But our z-score comes from the same place and it's doing the exact same thing. How far is this sample proportion from the hypothesized proportion, taking into account the standard error of p hat? Finding the p-value, we already know how to do, because once we have a z-score, we know what to do here, right? So because we've calculated a z-score, we need the z-table to find the p-value. So if we have a two-sided test, this is just a reminder, because the t-table, we just pick, right? Do we have a one-sided test or a two-sided test? So there's not a lot of thought that goes into it. Oh. My dog's having a bad dream, I think. Anyways, she's quieted down. So if you have a two-sided test and you use the z-table, then remember that you have to find the one-sided p-value and multiply it by 2 and pretend that it happened on the other side as well. That's all that's going on in the t-table as well, right? You'll notice that the one-sided p-values, if you multiply them all by 2, then you get the two-sided p-values, but it's just been done for you. Your conclusion is the exact same. So once you have your p-value, right, then you know what to do with that p-value. So once we have the p-value, we can draw our conclusion based on how the p-value compares to the alpha level, just as before. And I figured, hey, it doesn't hurt to have this summary here again, right? If the p-value is less than the alpha level, we have enough evidence to reject H naught in favor of HA. If the p-value is not less than the alpha level, we do not have enough evidence to reject H naught. Remember when I first introduced this and I said, whatever you do, just memorize this, right? And it's going to serve you well. Hopefully Hopefully it has, right? It's really important. I told you to write it on sticky notes, and even if it doesn't make sense, just kind of work through it, memorize it, read it all the time, commit it to memory, and then you can use it. Okay, nice. All right. So I think it's time for an example. Let me just check here. It is. Oh, and it's kind of a fun example too. Um, so when I had in-person tests, sometimes what I would do, was I would give options for the long answer questions. And so students had a choice of which one. They always had to tell me which type all of them were, right? But then they only had to answer one of them for marks. Okay, so on an exam, 156 statistics students were given the choice of long answer questions from the following types. One sample mean sigma known, which I have named known in the data set. One sample mean sigma unknown, which I've called unknown in the data set. Matched pairs, which I've called paired in the data set. And two independent samples, which I called two means. The variable for that is two means. They each selected one of the four questions to complete. That's not actually true. They picked two, but it makes the analyses way harder when students have picked two. So just ignore that. But just so you don't think that they had it so easy. But I've simplified the question here. So they each selected one of the four questions to complete. And then a summary of the question types chosen is shown below. Let me grab that here. Oh, and I might have to crop top. So this is data that I've collected. And so, of course, I have to read it in, and then I make a table of the type. And so 25 out of 156 students chose the sigma known question. 48 out of 156 chose the paired question. 40 chose the two independent means questions, and 43 chose the sigma unknown question. Right. So it might be easier to think about these if we talk about them in terms of proportions, right? Those raw counts are really hard to compare, I find, at least, or it can be. So we could use the raw counts, right? These are the number of successes in each of the categories, right? So depending on which category we're talking about here, and notice I'm saying category because this is categorical data, right? And that is what we're analyzing. And so we're talking about proportions here. So it makes sense to convert these to proportions, right? So we could use the raw counts, but it might be easier to consider the sample proportions of the question types chosen. And so for the sigma known, it was 16%, paired 30.8%, two means 25.6%, and sigma unknown 27.6%, roughly. Notice when we talk about proportions, we typically report them as percentages, but we definitely only use the proportion in our calculations, right? You don't want to be using percentages, but whenever we talk about proportions, we typically convert them to percentages. So here I've just kind of made up a question. There's lots of questions we could ask, like, is sigma known the least preferred question, right? Significantly least preferred question. That sounds weird. Instead, I've taken a positive spin here. So these proportions make us suspect that paired data is the preferred question type. right? It has the highest proportion out of all 4 categories. So then here's our question that we're going to answer. Is there evidence that paired data is the preferred question type? And then I've followed it with, are the assumptions for inference satisfied? That's just a reminder so that you don't forget to check the assumptions. Okay, so what I want you to do is just go through this question as best as you can. First, check the assumptions, right? And then go through and try it, and then I'll meet you back here. Sink or swim around here. I totally let you guys go try the question on your own without talking about how tricky finding your hypothesized proportion might be. Sorry. Anyways, maybe you found it, maybe you didn't. But because we have 4 different categories here, right? If there was no preference, what would you expect? You would expect 1 out of 4 or 1/4 of the students to pick sigma known, 1/4 of the students to pick paired, and 1/4 of the student to pick 2 means, and 1/4 of the students to pick sigma unknown questions, right? You would expect this kind of uniform distribution. And that happens a lot where it's kind of implied in the question. A really common one is if it's asking for the majority. A majority is over 50%, right? And so, yeah, it's just kind of sometimes it can be tricky to figure out what your hypothesized proportion might be. But you just want to assume, so for those hypothesized proportions, typically, unless there is some value given, typically, in the case of 4 different categories, then the hypothesized value would be 0.25, right, 1/4. If there were 2 categories, right, then the hypothesized value would be a 50-50 split, right? So 0.5 and 0.5. So it depends on how many categories you have. But you just want to assume, okay, if there's no preference, then we would expect, you know, 1/4 of the students in each of these 4 categories. Okay. So that's a little bit tricky, and that's why I have this question here, but I forgot I hadn't talked about it, so sorry about that. Anyways, hopefully you just kept watching maybe, and now you can take some time to try the question. Oh, do we have to? Yes. Or no, I'll never know, I guess. So if there's no preference for a specific type, the proportions for each will not be significantly different from 0.25. So we're expecting 0.25 in each category, which means that we're going to be testing the null hypothesis that P equals 0.25. Remember that we need this. We need this to check our assumptions. All right. So I've got it as step 0, right? Because we're checking assumptions. That's the first thing that we have to do. And then we can go through and actually do this hypothesis test. So first thing we have to check is if we have independent observations. Now, the question itself, right? It just says on an exam, 156 statistics students were given the choice. It actually doesn't say that they were randomly selected. That's okay, but it is something that we have to assume to do these analyses. And so what we say is we will assume that the sample of 156 statistics students is a random sample of all statistics students. Say that 5 times fast. The 10% condition, right? We will assume that a sample size of 156, so 156 students, is less than 10% of the population of statistics students. We will assume, right? We will assume, because we're checking the assumptions. or sometimes check the assumptions / state the assumptions. Sometimes we have to just be clear on all the things that we're assuming are true when we do our analyses, and it might not be correct, but or it might not be true that 156 is less than 10% of all statistics students, but that's what we are assuming. Okay, so we're just covering our bases here. So that's the independence condition. The second condition is the normality condition. Right, so the independent observations, and then we have to check normality. So since we're doing a hypothesis test and there's no mention of a confidence interval because we haven't quite introduced them yet for proportions, so then what we need to check is that we need at least 10 expected successes and failures, which we calculate using this null hypothesized value 0.25. So we expect, if it was a quarter split, right? So uniform distribution, there's no preference. People just kind of go and fall naturally in this uniform distribution. Then 156 students, a quarter of those would be 39, right? So then you would expect to have, right? And that's where this expected successes comes from. You would expect to see 39 students out of 156 who picked the paired data, right? If it was a quarter split, okay? And then for the failures, a failure in this case is anything but a paired question, right? Which makes up 75% of the data, or 0.75. So 156 times 0.75 makes 117 failures. Okay? Both of these are definitely over 10. And so that's usually, I like to kind of emphasize it with a fun check mark beside it, just to say, hey, it checks out. And they always will. That's not the issue. All of these conditions, we either say what we're assuming if it's not stated, or we just need to show that we know to check all the assumptions and what assumptions to check. So they always will work out. That's not the issue, okay? The issue is that you have to check them and you have to know to do it. So then, now that we've checked the independence condition and the normality condition, then we can say that the assumptions for inference are satisfied. And we are so happy about that. Whee! That's always going to be the case. But again, we still have to check them. Okay. Notice here, 156 is our sample size, right? So it's n times p naught. Notice that it having to be greater than 10, it means that we need to be able to detect at least 10 successes. And so what that's kind of checking or making sure isn't happening is that we're not checking for a tiny, tiny, tiny proportion. And if we are, we need a large enough sample in order to detect it, right? So something, so if we're thinking about a really, really rare occurrence, right, that proportion would be really, really, really small. So in order to detect something like that, you would need a very, very large sample. And so that's what this is doing. It's forcing that. Notice that the smallest sample size that you could possibly have is 20, right? Because if you need to have at least 10 successes and 10 failures, right, you're starting at 20. And so here, notice that the smallest possible sample size is 20, right? Because you need at least 10 successes and at least 10 failures. But if you have, right, you might need a larger sample to see those 10 successes and 10 failures, right? Depending on what the proportion is, right? So just keep I just wanted to mention that's kind of something that falls out of here. So in this case, a success is picking the paired type question. So we can find our sample proportion, right, which was just the 0.3076923. And so I'm going to round that to 3 decimal places. Usually the question will say how many decimal places I want it to. But 3 or 4 should be safe, right? Especially for your calculations. You don't want to do less than 3 because bumping this up to 31 is not a good idea, right? So you lose too much information in doing that. But if I go to 0.308, I feel like I've captured enough of that information there. So I'm going to use my sample proportion of 0.308. Now I'm ready to actually start my hypothesis test. So step 1 is, of course, state the null and the alternative hypothesis. What's nice is I've already done the null hypothesis. I've already decided that P equals 0.25 is the null hypothesis. And then because I want to know if the paired question is the preferred question, then what we want to know is did significantly more than 0.25 choose the paired question. Notice 0.308 is larger than 0.25. What we're testing is if it's significantly larger than 0.25, right? Once we take into account the spread. Okay. So now it's time to do the test, right? If you look back to your formula, then we need our p hat, which is the 0.308. And our hypothesized proportion is 0.25. And then, of course, our Q is 1 minus 0.25, which is 0.75. And our N is our sample size, which is 156. So there's nothing crazy here. And like I said before, there's actually less information that you need to do a proportion question. So, so that's kind of nice. So then if we do our calculations here, we end up with a Z of 1.67 once we round to 2 decimal places, right? So we have to round to 2 decimal places because our Z table has 2 decimal places, right? Whereas our T table had 3, so then we had to have at least 3 decimal places. Okay, we've got our Z score 1.67, so now we have to find our p-value. We go back to the Z table. So using the Z table, we find the area to the left, remembering that the Z table only gives us the area to the left, right below 1.67. So the area to the left is 0.9525, and maybe I'll just draw it out here. Right, so our Z is centered on 0, and we found a Z of 1.67. So this area here is 0.9525. Okay, but what do we want? We want to know the probability of being as extreme or more extreme, which puts us in the tail, right? That's the definition of the p-value. And so this is our one-sided p-value, right? So the area to the right is 1 minus 0.9525, which is 0.0475. Therefore, the one-sided p-value is 0.0475. And I frantically, I couldn't remember if I had it in here, which I'm glad I do. So I frantically mentioned it at the end of chapter 5, part 2. But here is, I want to illustrate how important it is that you don't put too much weight on the p-value, right? So a p-value of 0.0475 is less than 0.05, right? So there's no arguing that it is less than 0.05. But what if it's going to cost your company $1 million to reject the null hypothesis? Well, 0.0475 isn't that much less than 0.05, right? And so you don't want to be spending a ton of money or kind of risking lives with something that's so kind of borderline. It is less than 0.05, but I mean, we could change our alpha level and then it would be hooped. So be careful with p-values on the cusp of the alpha level, right? Think about whether there are consequences to rejecting H naught, right? So is it going to cost me $1 million or something absurd, right? In this example, rejecting the null hypothesis is inconsequential, right? If I go out there and I publish a paper that says the paired data question was the preferred question among statistics students, maybe I should write that paper. I need more data. Right, and so the preferred question is the paired data out of these four. That's not going to hurt anyone, right? And so I'm comfortable rejecting H naught in this case, right? But sometimes you want to take a step back and just make sure that you're not risking lives or hurting your company in any way. Okay. So I want to highlight that, right? So, but I also want to show you on the other end, right? If we had a two-sided test in this case, so in this case, we only had a one-sided test. So our one-sided p-value is the p-value that we're using. But if, so I was already, oh, wait, what happened? Back in action, I guess. Whoa, okay. I lost it. Where is it? Okay, we're back. Sorry about that. Okay, if we had a two-sided test, right, we would find our two-sided p-value. 0.0475 times 2 is 0.0950. In that case, if our alpha level is 0.05, now all of a sudden we're larger than 0.05. So then we would not be able to reject H naught. So this is why the two-sided test is the default, right? Remember on the formula sheet, I've got the not equal to as the default on in the alternative hypotheses. Right, and so this is the reason why, is because it makes it harder to reject H naught, right? So if you're ever unsure, then if you should be doing, less than or greater than or not equal to, if you're ever unsure, you should use a two-sided test, so a not equal to, because it's just harder to reject H naught. Okay, so I do want to highlight that as well. So this is why a two-sided test is the default, because it makes it harder to reject H naught. Okay. So if you're using R, then you can find the p-value using the prop test command, which takes X, which is, we usually use X. X denotes the number of successes. All right, so if you're struggling for some notation there, X usually denotes the number of successes, and as of course your sample size, and P naught is your hypothesized proportion. One thing I want to point out here is it's going to calculate a chi-squared, which we're not, so chi-squared is another type of test statistic, or it is a test statistic, but it's not something that we're covering in this course. It would be in a follow-up course. So there are other test statistics beyond Z scores and T scores. There's an F statistic, a chi-squared, there's lots, but the T and the Z are definitely the most common ones that we use, and so those are the ones that we focus on in this course. But don't be scared, they all behave the same way. We're all trying to do the same thing, right? We're all trying to find p-values, the probability of seeing something as extreme or more extreme than what we saw. Okay. So notice that this test does not calculate a Z, instead it calculates this. So this is a chi, Greek letter chi, squared, and it's spelled chi, C-H-I, but it's pronounced chi. Chi squared, but the p-values will be similar, so 0.04805. But remember, R is able to use the whole number. We use 0.308, right, which is the rounded value for p hat, and they're able to use the full value. So it'll be this very similar, but slightly different. Okay. That is really just for reference if you wanted to use software, but we don't have to. So for the conclusion, right, once we have our p-value, we're kind of back in our safe space where, okay, now I take my p-value, even though it's hard, right, now you can kind of work through it. Okay, if the p is low, then the null hypothesis must go. What does that mean? It means that if the p-value is less than the alpha level, right? So since our one-sided p-value of 0.0475, notice how I always emphasize what it is, just so that I can make sure that when I argue it, it makes sense. And I encourage you to do the same. So since our one-sided p-value of 0.0475 is less than our assumed alpha level of 0.05, it doesn't say what to use, so I'm using 0.05. That's our default. We have enough evidence to reject H naught in favor of HA. Therefore, right, you don't want to forget the conclusion in terms of the question. Therefore, there is evidence that paired data is the preferred question type. Okay. And here, preferred. I do want to highlight, right, the parts of the conclusion because it never hurts, right? So first you have to compare, thumbs up. First you have to compare your p-value to your alpha level. Then you have to state what your conclusion is in terms of H naught. Do you have enough evidence to reject H naught, or do you not have enough evidence to reject H naught? I repeat, I do not want to see conclusion in terms of the alternative hypothesis. It has to be in terms of the null hypothesis. Why? Because we did all our testing assuming the null hypothesis was true, right? So it's not until the very end that we can either reject H naught or fail to reject H naught. And then, of course, in terms of the question, there is evidence that paired data is the preferred question type. Cool. Okay. Let me pull up the, yeah, I'll get these sorted out here. Okay. So confidence intervals for one sample proportions are, I dare say, really easy. The reason for that is because we only need p hat, and of course we need the confidence level, but that will be given in the question, right? Make a 90% confidence interval, make a 95% confidence interval, right? And then of course we need the sample size. But after that, right, notice here's p hat, Z star, right, is from the confidence level, p hat again, q hat is just 1 minus p hat, and then n, right? And so there's really very little information that we need in order to construct a confidence interval. We still need to interpret the interval. So once we've built the confidence interval, we still need to interpret it. And we do it the exact same way that we were doing before, except we're talking about a proportion now, right? So we're not talking about the population mean. We're not trying to capture the population mean anymore. We're trying to capture the population proportion. Okay. So we'll dive right into an example here. So according to a 2012 Bank of Montreal RSP study, I don't know why I said Bank of Montreal, just Bank of Montreal RSP study of 1,000 Canadians 18 years of age or older, 67% of Canadians have a registered retirement savings plan, an RSP. A Statistics Canada study reported that in 1999, 57% of Canadians had an RRSP. Okay, so first thing I want you to do is read the entire question, and we'll read it together. But then the next thing I want you to do is read the question and try to figure out what's your sample size, what's your sample proportion, right? Sometimes you'll have to calculate the sample proportion, or in this case, it's been given to us, right? And so depending, there are kind of two ways that I could give you the information, right? So earlier, right, we found, now I can't remember if it was like 48 out of 156 or something like that, had chosen the paired samples. So then I give you the number of successes and the sample size, and then you have to find the sample proportion, or in this case, fine, we'll just do it together here. This is the proportion from the study, and the study had an N of 1,000, right? And the sample proportion was 0.67, right? P is a proportion, so P hat always has to be in the decimal form. Okay, so now let's read the questions together and see what we can do with the rest of these. So construct a 90% confidence interval for the proportion of Canadian adults who have invested in an RRSP in 2012 based on the survey. So we want to build a confidence interval for the population proportion in 2012. Okay, so that requires sample data from 2012. So it's all pointing us towards, okay, this is the sample information. And so far we haven't touched on the last sentence, but we will. All right, so part B asks, does this provide evidence of a change? Change meaning an increase or a decrease, it doesn't matter, right? From 1999 in RRSP investing among Canadians. Use the confidence interval to test the hypothesis. We can do that, right? We know how to do that. We've seen it before, right? Is the hypothesized value in the interval? If it is, you do not have enough evidence to reject H0. If the interval is consistently off the hypothesized value, then you have enough evidence to reject H0. So make sure that you check the assumptions, right? And what I want you to do is, because we're doing a confidence interval, you definitely have to check the assumptions for the confidence interval. And then we may as well, mostly for practice, we may as well check the assumptions for the hypothesis test as well. Even though it's not a formal hypothesis test, we may as well check it. Okay, so a little bit, well, I was going to say tricky, but there's really only one value here that's left, and that's the 57% of Canadians from 1999 had an RRSP. And so that, of course, is going to be the hypothesized value, because we want to know if there's been a change since then, since the time when 57% of Canadians had an RRSP. So I want you to take a moment and try to work through this question, checking the assumptions, and then working through the calculations, and then I'll meet you back here. Okay, so eventually in our hypothesis test, only because I highlighted what these two, the sample size and the sample proportion were, but I'll highlight here that H naught is that P equals 0.57, which means that therefore P naught is 0.57, right? All right, so here I've just listed the information, but now it's time to check the assumptions. So first thing we have to do is we have to make sure that we have independent observations, which is two-pronged, right? We have to have a random sample, so it's reasonable to assume that the sample was randomly selected. When I read the question, I'm pretty sure it doesn't say, it just says, according to a 2012 Bank of Montreal RRSP study of 1,000 Canadians, so it never actually said that they were randomly selected, but we are going to assume that they were, right? So we have to say that. It is reasonable to assume, and that's kind of my go-to. It's reasonable to assume that the sample was randomly selected. It is, but we have to say it. The 10% condition, and of 1,000, so a sample size of 1,000, it is less than 10% of Canadian adults. I can guarantee you that. Okay, so sometimes you have to kind of know about the population, and sometimes we just say that we assume that it is, okay? So then we can move on to the normality condition. And like I said, we're going to check both the confidence interval as well as the hypothesis test. So for the confidence interval, we need at least 10 observed successes and failures, right? And so in this case, I don't have the number of successes, but I have the sample size and I have the sample proportion. So then of course I can convert that to 670 successes, which is definitely more than 10. So I'll kind of mark that as checked out. And of course, the number of failures is 330. You could either do 1,000 minus 670 is 330, great. Or 1 minus 0.67 is 0.33 times 1,000 is still 330. So regardless of how you got there, you would end up at the same place, and it checks out. So it's definitely more than 10. For the hypothesis test, we need at least 10 expected successes, right? Expected in terms of your hypothesis. Right, so at least 10 successes, expected successes is 1,000 times 0.57, because that is your null hypothesized value. P naught is 0.57 from the question. Okay. Which of course, 1,000 times 0.57 is 570, which is more than 10. Whoop. And then 430 is also more than 10. Right. And again, what you could have done is you could have taken 1,000 minus 570 to get to this 430. If you're not a success, you're a failure, and vice versa, right? And so you can kind of move between these two that way. I will add here, usually I say it at the end. You don't have to, but I like to kind of put a stop to it, right? So therefore, the assumptions for inference are satisfied, right? Because we checked all those assumptions, and it feels like a lot in the beginning for sure. But once you've done it, it's not going to feel that bad anymore. Does that mean it gets easier? I guess that's what I'm saying. I don't know. I'm not sure it gets easier. You just get better at it, quicker at it. Remember, so we need our Z star for our confidence interval, but remember we use the t-table with the Z star row, right? We've done that so much now that I am expecting you to feel really comfortable doing that. And so for a 90% confidence interval, we've got a Z star of 1.645, right? And so now remembering that P hat is 0.67, and then you can just plug in your 0.67 everywhere, and slowly, methodically work through this square root here. And then where we end up is with a confidence interval from 0.6455 to 0.6945. That's half the battle, right? Half the marks. And then we have to interpret it. But it's the same interpretation that we did or used for the mean, except now we have to remind ourselves that, okay, well, we're actually talking about proportions here. So we're 90% confident that the interval from 0.6455 to 0.6945 captures the true proportion of Canadian adults who have invested in an RRSP in 2012. Because the sample came from 2012, right? So that's where our confidence interval, that's what our confidence interval is trying to say. Notice I used true proportion. True proportion is the population proportion. Population proportion. Okay, and let me just go back to remind myself of how the question was worded. It should be similar, but I think it was had some other stuff in there. Construct a 90% confidence interval for the proportion of Canadian adults who have invested in an RSP in 2012. And then it's followed up by based on the survey, but you can just cut that out for your interpretation because of course it's based on the survey. But so based on the survey was just to help point you in the right direction of what is your sample data. It's 1,000 Canadians from 2012. But now I want to know, and maybe I'll copy, oops, helps if I copy the right thing, right? Or the whole thing rather. So now, and I had to put my own gray box around it because I forgot to put it in when I typeset it, but that's okay. Isn't it beautiful? Does this provide evidence of a change from 1999 in our RSP investing among Canadians? Use the confidence interval to test the hypothesis, right? And so we want to test if P equals 0.57 or if there has been a change. Right, from 0.57. Our confidence interval was from 0.6455 to 0.6945. So since the confidence interval from 0.6455 to 0.6945 is consistently higher than 0.57, which is the hypothesized proportion, we can conclude there has been a change since 1999. And if we wanted to follow it up with, and it looks like the proportion has increased since then, we could say that. But you don't want to over answer a question because there's always a chance that you'll step in it. So I would just leave it here, but it looks like it's increased, right? Because this is kind of hard for students in the beginning, if you think about it as a number line, right, you've got your proportions here. And our confidence interval was from 0.6455 up to 0.6945. Right, and so here we're 90% confident we have captured P, right? So that's our interval. And because we're 90% confident that we've captured the true proportion P here, then the hypothesized proportion down here, P equal to 0.57, is outside that interval, right? And so because we're 90% confident that this is the P for 2012, that we've captured the population proportion for 2012, right? So it looks like things have shifted and it looks like they've increased, but the question only asked if there was a change, and it looks like there's been a change, right? And so that's how you use the confidence interval to test the hypothesis. So if this value were in the interval, then we can't reject that value, right? But because it's outside the interval, then we can reject H naught because we're 90% confident that P is somewhere in here for 2012, right? So that's how we use it. Okay. So good. We're going to build on the confidence interval to figure out how do we calculate appropriate sample sizes. And this is actually really useful, especially if you are tasked with collecting data for a survey. Then you need to know how many people do you need to survey to have results that are reliable. So let me just grab these here. And maybe I'll just take a moment to clean these up. Okay. So our sample size calculation, we've actually seen a sample size calculation before, right? With the Z-scores when we, in chapter 4, when we pretended to know sigma, which we can't really do anymore, right? Doesn't really make sense. But the same idea, we're going to use, we want to specify some margin of error that we want to be able to report in our findings, and some desired confidence level. And once we've established those, then we can go ahead and we can calculate what sample size we would need. So when designing a study about proportions, we'll need to calculate the sample size necessary to satisfy desired conditions on the margin of error, which we denote by m, a lowercase m, and the desired confidence level of our estimates. So using the margin of error, we can solve for m. And I've shown you how it unfolds here. And I've got it in the sidebar here. So remember that any confidence interval is the estimate. So you've got your best guess plus minus the margin of error. And so in this case, our margin of error is Z star times the root of P hat Q hat over N. So that's why I've said M. So here, M equals Z star times, oops, make a nicer square root here, times P hat Q hat over N. So if we're trying to solve for n is kind of deep down here in the square root. So we slowly have to unravel it. And so we can divide both sides by Z star, and then we can square both sides to get rid of the square root. And then we kind of do a switcheroo, right? In my mind, I multiply the n over to the left-hand side, and then I divide the m over Z star squared over to the right-hand side. And so, which flips the denominator and the numerator. And so I get Z star over M squared times P hat Q hat. If we go back to the formula sheet, that's on your formula sheet, right? So it's not something that I'm expecting you to remember or be able to do or anything. It's just, if you want to ignore this sample size calculation or this sample size formula and remember that this is your margin of error and solve for n, then that's totally fine. You can do that, but you don't have to. Okay. One thing to notice is that we've got P hat Q hat, but, right, so notice it requires the sample proportion, right, which is P hat. That's an issue, right? Because this hypothetical situation is before we've collected any data and we're trying to figure out what sample size we would need, right? And so notice that this calculation requires that we know P hat, which is fine if we have already collected a sample and we want to improve our estimate. That's an option too, right? However, When we initially organize a study, we will not know anything about the sample proportion, so that's when we're going to use P star Q star. Okay, and this usually kind of throws people off. So I'm going to highlight it, where P star is the sample proportion if you know it, right? So if you have a previous sample and you're trying to improve your estimate, then you can use P hat for your P star. Or just use a 50-50 split, right? If you have no preliminary data. Okay, and so here, if we have no preliminary data, and the reason for that is this: using P star equal to 0.5 gives us the most conservative estimate of the sample size required. And you can play around with it, right? But what you're going to end up, so you could play 0.5 times 0.5, right? A 50-50 split. 0.6 times 0.4, because remember, P is the probability of success and Q is the probability of failure. So they're always just going to add up to 1, right? And you can play with any kind of split that you want, but in the end, what you're going to find is that a 50-50 split gives you the largest possible sample size required, and that's what makes it the most conservative estimate. And so it's always safe to use 50-50. In fact, I used to only teach the 50-50 split, but I thought, what the heck? Let's just throw in the other option too, if you have preliminary data. Just like before, after you've solved for your n, so after you found your sample size, you're going to need to round up to the nearest whole value, because you can't sample a partial person or a partial manatee or a partial anything. And if we round down, then your margin of error would be slightly larger than what you said you wanted, right? And so we don't want to do that. We want to always round up. Okay. So I've got an example, and we're actually going to use the confidence interval and the question that we just did. So recall the question: according to a 2012 Bank of Montreal RRSP study of 1,000 Canadians 18 years of age or older, blah, 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 blah. No, 67% of Canadians have a registered retirement savings plan on RRSP. A Statistics Canada study reported that in 1999, 57% of Canadians had an RRSP. Can someone auto-tune that, please? Ding, ding, no. Sometimes I stop and I think, oh, it would have sounded pretty cool auto-tuned, I think. Anyways, I'll explore it. We found the 90% confidence interval. So we've already calculated this, right? And so I'm just telling you what it is again. And what we found was, right, remember that this is your M, right? That's your margin of error. And we calculated it, and we found that it was 0.0244602152. So here we found the margin of error to be roughly 0.0245. What if we wanted to reduce the margin of error to 0.01? Okay. So I've got two scenarios here. Determine the sample size required using the sample proportion as preliminary data, right? What does that mean? It means P star is 0.67. Yeah. So we're going to use a 0.67, 0.33 split. Okay. Part B, determine the sample size required, assuming you have no preliminary data. Then what do you use? Then you're going to use the 50-50 split, right? P star becomes 0.5 and 0.5, and Q star becomes 0.5. Because 1 minus 0.5 is 0.5. There you go. So give those a whirl, and then we'll meet back here and go through them together. Okay. So, right, I want to highlight the difference between these two because I tend to get, like I said, a lot of questions about it. So part A, determine the sample size required using the sample proportion as preliminary data. Okay, which means that using P star equal to p hat, which was 0.67, and a confidence level of 90%. So if you have a confidence level already, we're not going to change it. Otherwise, in a brand new question, it might say you want a confidence level of 95% and a margin of error of 0.03 or something, right? So we're going to keep the confidence level at 90%, but we can solve for, which means that Z star is 1.645 from before. Right? And then P star is 0.67, which means that Q star is 0.33. So once we go ahead and do these calculations, we end up with 5,983.02, right? Even though it's only 0.02, if you only went to 5,983, it wouldn't be a big deal, but it's also not that much more expensive to sample one more just to make sure that your margin of error is at least, or is no larger than 0.01. In fact, it would be a little tiny bit less than 0.01, right? But you don't want to go just to 5983 because then your margin of error would be slightly larger than 0.01, right? Which is not what you want. So we would need a sample size of 5984 Canadian adults. So now I want to determine the sample size required, assuming you have no preliminary data. So if we had no preliminary data, we would use a 50-50 split. And again, we want a confidence level of 90%. So again, Z star is 1.645. And we want a margin of error of 0.01 again, right? Same thing. But now this, we're pretending that, all right, we have not collected any data before. This is our first time and we're about to set out and we have no previous knowledge about the proportion, about the population proportion, right? That's what we're saying when we're saying, okay, well then we expect half of them to be successes and half of them to be failures, right? And so that's what we're saying when we have no preliminary data. We have no prior knowledge of the population proportion. So then what we find is we need, once we round up, and I should have had it here, we would need a sample size of 6766, so 6,766 Canadian adults, right? And here I'm just emphasizing that if I can keep it, have it on the same page here, when we use the sample data, we needed a sample size of 5,984. And then when we just assumed a 50-50 split, we needed a sample size of 6,766, right? So quite a bit larger. And notice that this is a more conservative estimate, right? Because the sample size is larger than it was before. And so that's why if you know nothing about the population, then you should use the 0.5, because that's going to give you the most conservative estimate for the sample size. Nice. Hey, good work, guys. Next up, chapter 6, part 2, which is for 2 sample proportions. We'll see you then.